In this set of notes, you're going to learn how to write electron configurations. And it's called Life on the Edge because we're talking about valence electrons, which are the electrons that are on the edge of the atoms. Just to review some of the models of the atom, there was the nuclear model, which was Rutherford's model, and it was designed after the gold foil experiment, where alpha particles were shot at a very thin sheet of gold, and most of the time the particles went straight through because atoms are mostly empty space, but 1 out of 8,000 times it would bounce off the small, dense, positively charged nucleus. Then there was the Bohr model, or the planetary model. Now they had a breakthrough that electrons were at fixed distances from the nucleus. Electrons can't fall into the nucleus because they have that fixed energy. And then there was the electron cloud model. This is the location of an electron is based on a probability. Okay, so this is a little revisiting of the cards that were in the activity from the other day. And you can see as you go down a group, you keep adding a shell. Hydrogen has 1 shell, lithium has 2 shells with electrons, sodium has 3, potassium has 4. So the big orange circle is the nucleus. I wish they had drawn it a little bit smaller. And then as you go across the group, across the period, you can see the number of electrons keeps going up by 1. So this has 3 electrons, beryllium has 4, 5, 6, 7, 8, 9, 10. And the outer shell for everything in group 8A, besides helium, because it's just a little guy, all of these have 8 electrons in their outermost shell. So just to review, core versus a valence electron. A valence electron is an electron found in the outermost shell of an atom, while core electrons are all the other ones that are inside. So, for example, how many valence electrons does aluminum have? Let's count them. 1, 2, 3. How many core electrons does aluminum have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now there's an easier way you can do this. You can look and see that aluminum is in group 3A, which means that it has 3 valence electrons. And since aluminum's atomic number is 13, you can do 13 minus the 3 valence electrons to get how many core electrons there are. So these are the shells, or also known as energy levels. These are the regions around the nucleus where electrons are likely to be moving. So this is the first shell, the second shell, the third shell, the fourth shell, the fifth shell, the sixth shell, the seventh shells. These exist for all atoms, but sometimes they're just empty. They don't have any electrons in them. And it's kind of like a ladder in that electrons can only move to the different shells. Just like if you're climbing a ladder, you can't stand between the rungs. So there are these fixed energy levels where electrons can live. And the innermost shell, n equals 1, is the lowest energy, and as you climb up or as you move further away from the nucleus, the electrons become higher in energy. What do these energy levels correlate to on the periodic table? The period number. Again, everything in period 1 has 1 electron shell full of electrons. Everything in row 2 has 2 shells of electrons. Period 3 has 3 shells of electrons. Period 4 gets a little bit tricky here, but all of these atoms have electrons in 4 shells, etc., 5, 6, and 7. Quiz. How many energy levels or shells would magnesium have electrons in? Since it's in the 3rd period, it would have 3. And here are magnesium's electrons. Because magnesium is number 12, it has 2 in the first shell, it has 8 in the second shell, and it has 2 in its outermost shell, which also makes sense because it's in group 2A. So that means it has 2 valence electrons. So it gets a little tricky, like I was saying, because shells actually have subshells. And then within subshells, there are orbitals. And there are 4 different types of subshells: S, P, D, and F. And I always give a little analogy that it's sort of like how people can live in different types of homes. So the shell would be like a city. For example, a small town in Washington. Let's just say, I'm trying to think of a small town in Washington. I'm not from here. I'm going to just go with Walla Walla. Okay? In Walla Walla, there's only a 1-bedroom apartment. There's only an S subshell. And an S subshell always has 1 bedroom, which can allow for 2 electrons to live. So every bedroom can have 2 electrons that live there. The next ring out, let's say that's a little bit bigger. How about Mount Si? Mount Si has 2 types of houses or subshells, S and P. So 2 electrons can live in the 1-bedroom apartment. And then now we also have a 3-bedroom apartment. So 6 electrons can live there because, again, each bedroom can have 2 electrons. Okay, and let's move out. The next ring, let's call that Bellevue. So Bellevue has still 1-bedroom apartments. It also has 3-bedroom apartments and 5-bedroom houses, the D subshell. Okay, and these aren't all listed here because this is a smaller atom, but again, it can have 2 that live in a 1-bedroom apartment. It can have 6 electrons that live in the 3-bedroom apartment, and then it can have 10 that live in the 5-bedroom subshell, the D subshell. And then if we go 1 out, let's just say Seattle. Seattle has mansions. F subshells have 7 orbitals, which means that they can hold up to 14 electrons. So this is repeating what I've already talked about, how every orbital can hold a maximum of 2 electrons. So here's exactly what I was talking about. So shell 1, again, that's Walla Walla, has an S subshell only. So there's only 2 possible electrons can live in shell number 1. Shell number 2, Mount Si, has a 1-bedroom apartment and the 3-bedroom apartment, so an S and a P subshell. So since there can be 2 electrons that live in each of these, it can hold a total of 8 electrons. Shell number 3, Bellevue, has the 1-bedroom apartment, the 3-bedroom apartments, and the 5-bedroom houses. So 10 electrons plus 6 plus these 2 makes 18. And then the 4th shell, Seattle, again has SP, D, and now the 7-bedroom mansion. So it can hold a max of 32 electrons in its shell. So this is a picture showing an S orbital. And here would be, for hydrogen, the probability of where that 1 electron would be. So you can see it's more dense in the center. Beryllium has 4 electrons, and it has 2 electrons in the 2s, so you can see more probability clouds. Boron is looks a little bit different because it has an extra proton, so it holds that second shell in a little bit closer. The P sublevel has a dumbbell shape. You can see how the probability cloud looks different. A dumbbell is also kind of has the shape of a peanut. Then it gets a little crazier from there with D sublevels and F sublevels. So there's a lot of different orientations of how those electron clouds can be distributed. There's another trend on the periodic table. If you're putting electrons in their homes, if you're talking about, let's see, this is where magnesium spot is right here. The last electron would be in an S subshell, meaning the highest energy. Okay, for all of these elements, their last electron lives in the D subshell. For this block, it's called the P block. except for helium is an exception. Helium actually belongs over in the S block, and then the F block is down here. Okay, we're going to see how that works in just a few minutes here. So just as a recap, what's the maximum number of electrons that can fit in each subshell? In an S, there can be 2, in a P, 6, in a D, 10, and an F, 14 max electrons. So there's another little cheat formula you can use to help you determine the maximum number. You can put in the shell number into this formula, 2n squared. So for example, if you wanted to know the max number of electrons in the 4th shell, 4 squared is 16 times 2 is 32. So that works for each of these shells. This is the filling order of how electrons go in their homes, we'll call them. So first is 1s, then 2s, then 2p, then 3s, then 3p, and wait, you'd think it'd be 3d next, but something interesting happens. The 4s subshell is actually lower in energy than the 3d. So it goes 4s, 3d, 4p, 5s, 4d, 5p, 6s, and 4f. And we won't go higher than that, even though, of course, you can go higher than that. This is another diagram that's showing the same basic idea here. See, it has the 4s lower in energy than the 3d. Quiz yourself. You identify 2 different electrons. One's in the 1st energy level, the other's in the 4th. Which one has more energy? I hope you answered the 4th energy level electron, because again, the further away an electron is from the nucleus, the higher the energy it has. Would an electron in the 4s or the 3d subshell have more energy? Okay, so going back to this, an electron in the 3d would actually have more energy. So that's kind of a tricky one. Alright, so let's get to electron configurations. Finally, what is it? So it's a list of all of the subshells that have electrons for that given element. For example, calcium's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. What the heck? The numbers that are superscripted tell you how many electrons live in this type of home. And the number out front tells you which shell it's in. So for example, for calcium in its very first shell has 2 electrons that live in an s orbital. It's just one little circle from the way that we've been drawing them with the x for the 2 electrons. Sometimes you see it as a square with an up arrow and a down arrow as well. And then calcium's next 2 electrons are in the 2nd shell, but also just one orbital in the s subshell. And then also still in the 2nd shell, there are 6 electrons that live in a p subshell. Then you move out to the 3rd shell, and so on and so on. So if we add all of the superscript numbers, it should add to 20 because calcium's number 20, and it does. Okay, so let's look at another way to do these problems. Let's keep talking about calcium. Okay, so the way that I taught this in class, and if you're missing, you'll have to get a copy of this, but we basically took a highlighter and we highlighted from here all the way down to here, and then we took another highlighter, or we used the same highlighter and we highlighted from here down to here, and then we took a highlighter and highlighted from here down to here. Okay, so if we're trying to write out the electron configuration for calcium, you always start like you're reading a book. So you start at hydrogen and you move across the period, so all the way over here, and every time you hit that highlighter, the double line on here, you write down what you see on the edge of the square. So if we're trying to get to calcium, first we write 1s2. Okay, then again down to the 2nd row, it's like you're reading a book. Boom, you hit that highlighter again, 2s2. Keep traveling across, boom, you hit this, you write down 2p6. Keep going, boom, you hit this double line, 3s2. Keep going, boom, you hit this double line, 3p6. Keep going, boom, you finally hit calcium, 4s2. And if you look back at that last slide, you'll see that that matches its electron configuration. The only thing weird that happens is, as you go across, and if you were to do something larger like iron, you'll notice that even though it's in period 4, it skips down a shell. So these are all 3D to the something. Okay, so just be aware of that, and then it pops back up to 4s here. Again, that's because the 4s and the 5s and the 6s, for that matter, are all lower in energy than the D subshells. That's just how it is. Okay, and you also might be wondering, where does the F block come in? Okay, so there's an Aufbau diagram that kind of shows you where that would start, but I want to let you know that that's not something that we have you write electron configurations for. If you continue on to AP Chem, then you may, but that's beyond the scope of this course. Alright, so let's look at more examples here. Hydrogen, super easy, 1s1. Okay, so if I take a second and I go back, that's just literally what's on hydrogen's square, 1s1. The next one was carbon. Okay, so if we're working for carbon, we go across, boom, we hit this double line, 1s2, keep going, keep reading like a book, boom, we hit this, 2s2, and then to carbon, 2p2. Just to review what that means again, it means that those are where carbon's electrons are. It has 2 electrons in the first shell, and it has a total of 2 plus 2, 4 electrons in the second shell. Okay, so for each of these examples, it's the same thing. Moving across, writing down what you see every time you hit that double bar or that highlighter mark. Okay, this is that Aufbau diagram I was referring to. If you ever forget the order of how it goes, you can draw yourself a little Christmas tree. So 1s, 2s, 3s, 4s, 5s, 6s, 7s, and then go over and skip, because there's no 1p, skip down 1, 2p, 3p, 4p, etc. Then there's no 3p, so skip down 1, 3d, 4d, da 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 da, and there's no 4d, skip down 1, 4f, blah 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 blah. I'm sorry, I didn't mean to say there's no 4d. There is a 4d. There's no 3f, is what I meant to say. Anyways, you draw this out, and that's not hard to learn. And if you start from the upper right and you start drawing arrows to cross out these, it will show you the filling order. So it goes 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, and this is where the 4f comes in. So after 6s, if we're to go back and look at this, 6s right here, this is where the F's would come in, which makes sense because 57 through 71 is that next spot there. Okay. We did a couple more practice problems in class, so I encourage you during these notes to pause and see if you can do these before you see the answers, writing out bromine and writing out silver's configuration. Okay, and now you're going to be really happy about this. This is a shortcut to writing an electron configuration. How does it work? So you always use the preceding noble gas as a placeholder. Example, if you're writing out the electron configuration for sodium, you look at the last noble gas that occurs before sodium. So sodium's number 11. So of all of these noble gases, the one that exists right before it is neon. And so you cheat. You skip writing all this other stuff until you get to neon, and you just put neon in brackets and continue from there. So for sodium, it's just neon in brackets 3s1. So check it out. Instead of writing all of this, you just get to write neon 3s1. Okay, let's look at another example. They want you to write one for scandium. So scandium is right here, number 21. What's the last noble gas before scandium? So we got to go backwards. It's argon. So you put argon in brackets and then 4s2, 3d1. That would be the noble gas configuration. And we're right, it's right there. Alright, so practice. Write the noble gas configuration for barium. Pause the video and try to do that. The answer is xenon in brackets 6s2. You got to skip a lot for that one. And for selenium, it's argon in brackets 4s2, 3d10, 4p4. If you're supposed to write noble gas shortcut for noble gas, you actually just get to put the noble gas itself in brackets. Alright, how about this? How many valence electrons are in the following? Okay, let's take a look at this. This is the first shell, second shell, third shell, fourth shell, and then there's the third shell, fourth shell. So which is the outermost shell? The fourth shell. How many are in there? Well, there's 2 here plus another 4. So that makes 6. So you add those 2 together, and this is selenium. And that is it for the electron configuration notes.